Linear programming, just to give you a little history, came out of our efforts in World War II. The problem that people face is that a lot of times you have to work under real world situations in which you don't have an unlimited amount of resources, etc. When they're building tanks and planes, stuff like that, they had a limited amount of means of production and they wanted to maximize the output of war goods. So it's a relatively new field. I mean, as far as the rest of the math that you're learning, at least this is in the 20th century. Most of the other stuff that you've been learning has been around for centuries, if not thousands of years. So the idea is this. You have this real world problem and you're trying to maximize something. In this case, we're trying to maximize the profit that a farmer makes. But our farmer is working under some constraints. So we're going to let X be the number of acres of soy, and Y is the number of acres of corn that you plant. Now, our farmer has a maximum of 20 acres of corn. So that gives you a constraint that is X plus Y is less than or equal to 20. I said maximum acres of 20, maximum of 20 acres. So the number of acres of soy and corn that you can plant is at most 20. So that's a constraint that you have to work under. Another constraint that you have to work under is you've only got so many tons of fertilizer available. Now, I chose these numbers not because they're realistic in any way, at least I hope not, but rather just because the numbers work out good. So you need 4 acres, or 4 tons of fertilizer per acre, and 3 tons per acre for corn. So that gives us another inequality. 4x plus 3y is at most 72 tons. Now our goal is to try and maximize how much money you make. Now, under the prices that are given here, soy is worth $220 an acre, corn is worth $190 an acre. So you might say, well, why not just plant everything soy, right? You make $220 an acre. The problem is you'd run out of fertilizer. So you might need to do some kind of a hybrid. There's a couple constraints here that are implied but not really stated. And that is X has to be greater than or equal to 0 and Y has to be greater than or equal to 0. So, like I said, a couple constraints that are implied. These are called natural constraints. And they won't be stated, but they're important because this restricts your solution to the first quadrant. It has to be someplace here in the first quadrant. Now, as far as the rest of this is concerned, when graphing these things, what I always suggest to my students is that you plot the X and Y-intercepts. So as far as X plus Y equals 20, let's work with that one. If X is 0, Y is 20. If Y is 0, X is 20. That's pretty easy. And that pretty clearly pins down this line as being the line X plus Y equals 20. Obviously, our other line is the 4x plus 3y equals 72. But it's still worth our time to try and figure out what the X and Y intercepts are because we're going to eventually need some or all of those points. If X is 0, Y is 24. If Y is 0, 4x equals 72. 72 divided by 4 is 18. So there's your other equation. 4x plus 3y equals 72. Of course, that's just graphing the equalities. Remember, these are inequalities. So what else do I have to do beyond just graphing the equation? Yeah, I have to do some shading here. So let's take a look at what's going to happen when we start thinking about the shading. Let's start with x plus y is less than or equal to 20. And we'll test 0, 0 is my favorite test point, so we'll test 0, 0. 0 plus 0 less than or equal to 20. True or false? True. So you're going to shade below this line. And let's just kind of draw a couple little arrows here below that line. Let's take a look at the other equation. 4x plus 3y equals 72. So test 0, 0. Let's shade that this way. It should be less than or equal to. So 4 times 0 plus 3 times 0 is less than or equal to 72. True or false? So where am I going to shade for this line? We tested 0, 0. Where do I shade? Kind of above or below? I don't have a whole lot of unanimity in this. Above or below? Below. Below, there we go. Thank you. So below on both of them. Now, that one's here and that one's here. See if you can't use some thinking to try and figure out where these shaded regions are going to overlap. Now, your solution is just going to be restricted to the first quadrant, which is why I've drawn my graph as I did. But try and figure out what that shaded region looks like when it overlaps. Try and shade it. In fact, while you're doing that, I'm going to shade it off camera, give you a chance to work on that. Okay. You should get a shaded region that looks something like this. All right. It's the region closest to the to the origin. Now, that's great. What this represents is our feasibility region. Feasibility region. I always forget. Is that an I? Feasibility region. All right. So it's spelled phonetically. So these are all the different combinations of crops that you can plant. You could plant everything in terms of corn, or excuse me, in terms of soy, or you could plant everything in terms of corn. The downfall of planting everything in corn is that it doesn't make as much as soy. The downside of planting everything soy is that you're leaving 2 acres unplanted. So, what are you going to do? Well, to try and decide, keep in mind what we're trying to do is we're trying to maximize our profit. So our profit comes from how much corn and soy we sell. So let me call that P of X, Y. Our profit depends on 2 things. It depends on X and it depends on Y. How does it depend on X? Well, how much revenue do we generate from selling an acre of soy, acre worth of produce from soy? So 220X plus 180Y. So that's your profit function. So the question is, what combination of points in here maximizes this profit function? There's a lot of combinations. You could plant 0, 1, 1, 2, 2, 3, etc. And it'd probably take you a long time to figure out all the different combinations and test them all. But there's good news. There's really good news. We don't need to test all the points. We're just going to test the so-called corner points of our feasibility region. It's also called the solution polygon. So all we need to do is test these points in our profit function, in our objective function. So that's 0, 20. Here's 18, 0. This is 0, 0, and I'm missing 1. And let me tell you a test question for yourselves. Describe for me the different ways that we have to find this point. Now, you can kind of probably look at it based on the graph and figure it out that way. But what are the ways that you could have, in absence of the graph, to find this point of intersection? So find this point by, and you should be able to think of at least 4 or 5. So substitution. So you're going to work with these two equations and do substitution. What else? Elimination. Second calc, so with the graph. And you can do that with, second calc. Sure. That's fine. What else? Well, yeah, we'll call that the graphing method. But what else? There's at least 2 more that you've learned. Now, you probably wouldn't go there because it'd probably be more work than these other methods. Cramer's rule, all right, which is like squirrel hunting with a bazooka, but, it would work. One more. What else could you do?
With a system of 2 equations, it's not too bad.
I think somebody whispered inverse matrix. Yeah. So there's a lot of ways you can find the solution to that 2 by 2 system of equations. Can anyone just use the graph? Tell me what the solution is? 12, 8. Now, you can be sure of that because if you come up here, 12 plus 8 equals 20. 4 times 12 plus 3 times 8, 48 and 24 is 72. So 12 and 8, bless you, is our solution. You might have also looked down here and noticed that there's a 12 and 8. All right, but that's not exactly in the spirit of things. So let's see here. 220 times 12 plus 190 times 8.
4,160.
Sweet. So that's the maximum profit that you can make under these constraints. Okay. What I want us to do is I want us to look at things on whatchamacallit. Yeah, on Desmos. So let's take a look at what this problem would be like on Desmos. And like I said, and I haven't put this together, but I got inspired last night to think, you know what? I'm tired of teaching this the same way. We've got a lot of technology available to ourselves. We should be able to take advantage of that. So let's go over to Desmos and see what Desmos can do for us. So does everyone take out their laptop or some device that it can connect to Desmos? If you don't have one, make a friend. All right. All right. All right. Let's type in some of this stuff here. So, for instance, now I'm not going to type in the x is greater than 0, y is greater than 0. I just know that that's going to mean we're going to be in the first quadrant. Let's type in x plus y is less than or equal to 0, or less than or equal to 20. X plus y. And there's a button on this form down here that types in the less than or equal to 20. Now I can kind of zoom out a little bit on this, and I get a graph that looks like that. If you go to the graph settings and hit projector mode, it'll make things a little bit more crisp, a little bit easier to see. So everyone got this one? No. Let me see it. Let's type in the other one. 4x plus 3y. Again, less than or equal to 72. Now you can change the color on your graph. I'm going to change that to be red again. That way it's just a little easier to see where these things overlap. The nice thing now is that I can see my corner points. Whoops, I must have typed in something wrong if I get 10, 10 there. Oh, 70, how about 72? There we go. So there's a point. So I can see all the vertices of my solution polygon. So that's cool. Yeah, I'm not sure what's going wrong with this. Sorry. So the nice thing is that you can get these points pretty quickly and pretty easily. So let's apply that to a different problem. But is everyone able to get something close to this on their device? Yes? Okay. It's a good time to get some help. All right. So let's try working one that's on your handout. I'm hoping this on the, let's see, have I passed this one out yet? Maybe not. Okay. Let me pass out another handout then. Four, 5. Okay, so let's write down the conditions for our next example. Our objective function is going to be q of xy equals 70x plus 82y. We're going to have conditions on our linear programming problem of the following. X and y are both greater than or equal to 0. That just tells me that my solution is going to be in the first quadrant. We also have x is less than or equal to 10, y is less than or equal to 20, and a couple more things here. X plus y is greater than or equal to 5, and x plus 2y is less than or equal to 18. So a lot of conditions here. And when I've taught this class before for like a Math 1150 class, it's a real pain. But we're not going to do it by hand. We're going to do it with Desmos. So let's see what we can do with Desmos to make our lives a lot easier on this problem. I'm going to clear out my old functions and start typing in the new ones. So let's start with the easy inequalities first. And here's where you have an advantage over your calculator. Your calculator cannot do this one. X is less than or equal to, what is it, 10. Y is less than or equal to 20. Now I'm going to put all of these in the same color. That way it's a little bit easier to see where they overlap. Let's keep going. x plus y is greater than or equal to 5, or x plus 2y, I should, no, x plus y. I was right the first time. X plus y is greater than or equal to 5. And one more. X plus 2y is less than or equal to 18. Yeesh. So let me zoom in here. Now we want to look in the first quadrant in the shaded region there and find where this all overlaps. So here, 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 and here. So these 5 points of intersection are the ones we have to test. So what we could do is plug all those points into the function for q. So I have q of 0, 9, q of 0, 5, q of 5, 0, q of 10, 0, and q of 10, 4. So those 5 points are what I have to test in my objective function. One of those points is going to maximize our objective function. So it's just a lot of grunt work here. 70 times 0 plus 80, 82 times 9. So that's what, 738? 70 times 0 plus 82 times 5 is 410. 70 times 5 plus 82 times 0 is 350. 70 times 10 plus 82 times 0 is 700. And 70 times 10 plus 82 times 4, let's see, 1,328? No, 1,028? Someone check me on that one. Jeff. Oh, man, so disappointed.
I had a lot to write down.
82 times.
1,028 is
Yeah, all right. Now, it depends on what you're looking for this function. There's 2 points that would be of interest, typically. Either a maximum or a minimum. So the maximum occurs at 5 and 0. Excuse me, the maximum occurs at 10 and 4, and it's 1,028. The minimum occurs at 5 and 0, and it's 350. So it depends on your objectives for these types of functions, but you can get, a couple possibilities here. The nice thing, like I said, is that you don't have to test the infinite number of points that are in your feasibility region. All you have to test is the corner points there. And so it makes it a lot easier than doing this problem completely by hand. How are we doing on the linear programming? Are you okay with finding those things on Desmos? If you just take your cursor and click, it'll find these points of intersection. So you gotta tap on it. It's much easier to do with a whatchamacallit, a mouse. Alan?
How do you know which points to pick from again?
Good question. We want to find where the shaded regions all overlap. So I'm not sure how well you can see it from your seat there, but this is the darkest region, and that's where the shaded regions all overlap. So that's your feasibility region. Okay? I probably won't give you like 5 or 6 conditions like this problem does. I'd give you like 3 or 4. Anything else on this one?
So are we going to be using Desmos then on the test?
Probably what I'll do is I'll bring in my laptop. Maybe I can borrow one of your laptops and let you guys just use Desmos on that portion of the test. Now keep in mind, what you're going to have to do afterwards, after you find those points, is run them through the objective function. But that's just, some calculations. Yes, sir?
Out of those, how do you know which one's the big?
Well, it depends on what the problem is asking. But this one is your minimum, and this one's your maximum. So, certain problems ask for you to minimize something. Other problems ask for you to maximize things. It depends on the problem. On the back of your handout, you're trying to do a couple different things here. For problem number 8, one is to maximize profit. Another one is to minimize cost. So it depends on the functions you're working with and your objectives. But you can do either one. Now, once you have that solution polygon and you run it through your objective function, you're guaranteed to get a minimum and maximum at one of those points, at least one of those points. Okay? This problem is funny. It's from an older book, but it cracks me up. You're talking about manufacture of calculators. Okay, cool. But you've got a scientific calculator and a standard calculator. Oh, what's a standard calculator? So just do like add, subtract, multiply, and divide or something like that? I don't know. But it seems pretty dated.
Like Windows.
Yeah, the little...
Scientific, yeah. You can go up in the corner. change
Well,
it to-
the cool thing with your iPhone is if you do your calculator and then you turn it, then all of a sudden it becomes a full-blown scientific calculator, which is kind of cool. Okay. I suggest you do a couple extra problems in homework. I've got you a good head start if you wanted to do problems 8 and 12 here, because on the front side, your graphs are pretty much almost already done for you. So I'd suggest you just finish up problems 8 and 12 for homework. That's 10.9, yes.